speak about decay of Fourier modes for the solution of the Navier-Stokes system. Please welcome.
Thank you very much. So it will be just the ordinary talk with formulations, proofs, unsolved problem, questions, and all that. So just if you have other questions, please just don't hesitate to ask them. So as you can understand from the title, main subject today is Navier-Stokes system, and in particular two-dimensional Navier-Stokes system for incompressible fluids. And this system consists of three parts, which I shall write in the order which is mostly convenient for me. So the first one is this Navier-Stokes system is written for two functions, u1, u2. Each of these functions is function of two variables, x1, x2, and time, and then also the pressure term, P. P is also function of this variable. So the system of equation is just the following. So the divergence u, which is just du1 dx1 plus du2 dx2 equals to 0. In my opinion, this is just one of the most important parts of the whole system. Then the second is the equation of dynamics, which says that duj over dt plus the sum of uk duj over dxk equals to Laplacian of uj minus dp dxj. So this writing means that the viscosity equals to 1 and no external forcing. So if we would have external forcing, then there will be some additional terms, and we don't assume that they are here. And then the set is just boundary condition. So this system of equation, in a sense, is rather inconvenient, just because it has just this pressure term and its role is not clear. So the way to make it simpler is just the following. We consider omega, which is called the vorticity of u. And then for omega, we have just one equation, d omega over dt plus u1 d omega dx1 plus u2 d omega dx2 equals to Laplacian of omega. And you can see from this formula that it does not have the pressure term. On the other hand, the connection between u and omega follows from this relation, and it is very highly non-local. In other words, it's better to think that u1 and u2 are just rather complicated functions of omega. We shall just fight with this a little bit later. So the next step is not so often done, but it's very convenient. We shall consider not the function vorticity, which is here, but the function psi, which is called stream function. And this stream function is connected with our equation in the following way. u1 is just minus delta psi dx2, and u2 is delta psi of dx1. By the way, are the letters not too small? Just can you? Good. So just the reason why it is convenient to have this function psi is that if we have just function psi and find u1 and u2, then they always satisfy incompressibility condition. There are just many other advantages of stream function, which I shall just write. By the way, I want also to write that omega is the Laplacian of psi. So in principle, everything can be expressed through the stream function psi. And I want to spend some time trying to convince you that psi is a very useful function. So for example, assume that we consider the case of periodic boundary condition, and then psi is periodic function of x1 and x2. And suppose that at some point x, psi has maximum. Psi of x1, 0, x2, 0 is local maximum or minimum, does not matter. So this expression u1 and u2 are just sometimes called perpendicular gradient. They are not gradient, but they are perpendicular to the usual gradient. If we have just local maximum at some point, then the gradient is just perpendicular to the local stream, to the local level sets of this function. They look like this. But perpendicular gradient will be just in this case directed along this level sets. Therefore, near the points of maxima or minima, we have just what can be naturally called vortices, but these are not vortices in the ideal fluid which are usually studied, but they are just vortices in the viscous fluid, and I shall show you that they are also very interesting in several cases. So just from this description, you can see that extrema of this function psi describes the behavior of maximum. And then the question is, what will be the behavior of this extrema when we consider the dynamics in time? We can even consider the simplest case. So I shall just talk about the dynamics corresponding to omega, to psi a little bit later, but now let's consider a simpler case. Assume that we have an interval 0, 1, and assume that we have at t equal to 0, and at some point, some function of one variable which has a local maximum in this point, and this is a point of degenerate maximum. In other words, if we consider the expansion of this function near this point, then it starts from the term of degree 4. And then let's consider the simplest equation, the heat equation, delta psi over dt equals to the second derivative of dx squared. So a theorem which was proven recently by Princeton, by student from Princeton University, Oliver Conway, says the following: if we have this dynamics, then for arbitrary positive t, the maximum becomes non-degenerate. In other words, we could assume that there are bifurcations such that as a result of this bifurcation, there appear two local maxima and one local minimum. This bifurcation do not happen in this equation. So if you use the terminology from the theory of bifurcation, then our differential equation determines to us some deformation of the initial condition. There exists the notion of Versal deformations, which is often used here. According to Versal deformation, the deformation which appear in some problem is just describe all possible bifurcation. So this is not the case in this problem. In other words, if we consider deformation which follow from the equation, which is here, then the deformation will just produce only non-degenerate maximum. So this is a part of more general theorem, which was proven by the same person, and it works also in the multidimensional case. So if we just consider delta psi over dt equals to the Laplacian of psi, and we assume that initially at some point maximum is degenerate, then under solution of this equation it becomes non-degenerate for arbitrary positive time. Even more, we can consider not only heat equation, but we can consider diffusion reaction equation of the following form, and the statement, yes?
How did you go from vorticity equation to the heat equation?
I shall answer to this question later. Just now I want to consider the evolution of vortices. And for the equation for these vortices, I take the simplest equation. So the simplest equation is the heat equation. Then
one more. Why these don't contradict maximum principle for heat equation, maximum inside the interval?
Because just in principle, you can have just, as a result of the evolution, you can have just several maximum.
But you have maximum principle for heat equation?
Yes.
And why your maximum inside the interval?
But this is probably local maximum, not
It's local maximum.
Well, local, it does not matter. Maximum, local.
Yeah, it's local near this point.
Yeah, I know.
So then I said that this statement holds for just diffusion reaction equation, and also it holds if we consider the equation corresponding to Navier-Stokes system. I shall explain later what will be the equation for corresponding to Navier-Stokes. But I want to give you an example when the statement is not true. Namely, let's consider the equation delta psi over dt equals to minus square of Laplacian psi. Yeah. And in this equation, it might happen that there are just some non-trivial bifurcations. I have with me just picture which was just produced by my co-author Dong Li. Later I shall show it in more detail, but it just says the following, that if we consider the unit square and we consider this equation, and initially at t equal to 0, our function has the degenerate maximum at some point, then for sufficiently small times, the result of this calculation were done in the case of some symmetry. Therefore, there just appeared four local maxima and one minima. Something like this. Yeah. So I want to say that depending on the equation, various types of bifurcations corresponding to stream function can happen. So now we come back to Navier-Stokes system. And I want to write down the equation Navier-Stokes system using the stream function. As you will see, this is just mostly convenient for me. So, let's consider periodic boundary condition. Periodic boundary condition is a very special case. What happens in the case of periodic boundary condition does not happen in other cases, and actually even it is somehow misleading because in other cases the properties of solution can be more complicated. You will see it. But in the case of periodic boundary condition, everything is just quite simple and quite well. So we assume that our periodic boundary condition have period 2 pi with respect to each variable, and I write psi in the form of Fourier series h mn of time times e to I m x1 plus n x2. Then if we have this function psi doesn't matter. If we have this function psi, then we can write down u1 as just minus I, the sum of h m n times n e I m x1 plus n x2. In the same way, u2 is just I, and then the sum h m n m e I m x1 plus n x2. And then we write down the expression for vorticity. Omega is just the Laplacian of psi, and this is minus the sum of h m n m square plus n square e I m x1 plus n x2. And so we have the equation for vorticity, and we can just substitute all this expression, and what we shall have is just the following: the sum of h m n dot, which we shall have from this term. From this term we shall have just convolution plus the sum over m1 plus m2 equals to m, n1 plus n2 equals to n, and then here we shall have just n1 h m1 n1 times m1 h m2 n2. Then plus the same term for just corresponding to this product, which I shall not write, and then it is just equals to, and then maybe write it, and plus m square plus n square times h times e to I m x1 plus n x2. And this is 0. From this expression, we immediately derive an infinite dimensional system of ordinary differential equations for these coefficients h m n. So h m n dot plus the sum of n1 h m1 n1, m1 h, I'm sorry, m2, m2 h, m2 n2, and then plus the sum of m1 h, m1 n1, n2 times h, m2 n2, and then plus m square plus n square times h of mn. And this is equal to 0. So this is not, yes?
So is the last term Laplacian of omega?
Yes.
So it should be m squared plus n squared squared, right? It's Laplacian of the last.
Yeah, you are right, yes, thank you. So just HMN, no, just I write down, I shall make the following just corrections. I shall use omega, but I shall write it as just the sum of GMN. And write down the equation in terms of Fourier coefficients for the vorticity, GMN. Then this question will not arise, and everything will be just simpler. GMN plus G, and then also G. And then here. So this is, as I said before, this is a nonlinear system of equations.
Now you have to divide by.
So what?
Last stage. So convolution is h and g.
Convolution is, no, just, no, here I just have, yeah, you mean just U1. Okay, just I shall write down the equation. So G is just the convolution of vorticity, and here we shall have just G. So omega is just then U is just one, or so stream function is just the sum of H, and then U is just the sum of M, just say N, H, and then if this is just the sum of N, G over M square plus N square. Yeah, that's, yeah. So this is just simple formulas. I just have it somewhere here, but cannot find it at the moment, but just the final equation has just so just this is just a derivative of vorticity, and then this is just velocity. So just I should write here m1 square plus n1 square, and then n1. Then it will be just velocity, and here it will be just m1, also m1 square plus n1 square. Yeah. So
The
this.
last term is g. The last term, g of omega.
Yeah, this should be G. So this is an infinite dimensional system, rather simple, and it has also one important property by which two-dimensional fluid dynamics is different from three-dimensional fluid dynamics, and it is just the following. If we introduce omega, which is just the sum of G square of Mn, the L2 norm of vorticity, then if it is a function of time, then omega of t is less or equal than omega of 0. So vorticity always remains bounded if at t equal to 0 it was bounded. And this is very important property. I shall just formulate you two theorems which are valid for this system, and they follow only from the preservation of vorticity. By the way, this norm is called entropy. So sometimes this equation is called entropy inequality. So, two theorems. Theorem 1 says the following. Assume that at t equal to 0, the coefficients gmn and 0 satisfy the inequality. Then they are less or equal than some constant a over m square plus n square to gamma over 2, where this power gamma is greater than 3. Actually, 3 is rather important in this inequality. I don't know what will happen if gamma is less than 3. Then there exists some absolute constant c, which can be calculated, but it depends also a little bit on the initial condition, so that the solution g of mn and time t is less or equal than this constant c times a over m square plus n square to the same gamma over 2. In other words, if initially the Fourier coefficients of our function psi satisfy some power, then this decay of the power remains for all positive times. Yeah. And then theorem 2 says gives even a stronger statement. So I shall formulate it in the following way. Assume that we have some axis time t and the function f, and this function is linear for t less or equal than t critical, and then it is constant. Then under the condition of theorem 1, this coefficient gmn of t satisfy the following inequality. It is just this constant c times a times e minus f of t, and then square root of m square plus n square. Yeah, and here it is more convenient to write m square plus n square to the power gamma over 2. So the meaning of this theorem is just the following, that if initially our coefficient g decay is some power of mn, then immediately after all positive time they start to decay exponentially with the norm m squared plus n squared. And this is just the right decay, in the sense that there are no reasons to expect that here one can have just a higher power of m squared plus n squared. And this shows that the solution to our equation are just rather far from solution of the heat equation. In the heat equation we shall have m squared plus n squared. But it's not the case here. The actual decay will be just simply exponential. So several words how the proof of this theorem goes. I shall explain first the proof of theorem 1 and then explain the changes which are needed for theorem 2. For theorem 1, the proof is based on the so-called trapping argument. Trapping argument is just the following. Suppose that in some infinite dimensional space we have that a bounded convex subset, and we have some point some point y inside this subset. And then our system of differential equation determines vector field everywhere inside this subset. And suppose that this vector field is directed everywhere at the boundary inside this set. Then, if this is the case, then there cannot be trajectory. Then every trajectory which goes from some point inside set remains inside this set. It cannot come to the boundary, because if it comes very close enough to the boundary, then it must return back to this set. This trapping argument was used in our joint paper with Jonathan Mattingly. And myself. And slightly different argument was used also in the paper by Fourier and Temam, which has even stronger results than our paper, and in addition it was published 10 years just earlier than our paper. So that our argument is slightly more geometric than their paper. So what will be just this subset, and what will be the vector field which appear in our problem? Vector field is just exactly consists of the right hand side of these coefficients which are just here. Yeah, this is a system of ordinary differential equation. In a different language it means that this is a vector field and this is the vector field which we shall use in our case. So what will be the subset? The subset will be just the following. We consider a set of sequences GMN which are less or equal than the constant C times M over M squared plus N squared to the power gamma over 2. Constant C will be chosen sufficiently large in connection with the entropy, which we have just at t equal to 0. Then suppose that our statement is wrong, then it means that at some value m0, n0, in this inequality we have just strict equality, which we can assume that this is CA over m squared plus n squared to gamma over 2. And for all other values of m and n, we have the inequality. Then, using the right-hand side of our equation, it is possible to prove that the viscous term, which is here, dominates the nonlinear term. And viscous term is just negative. You can put it in the right-hand side. And this term are bounded, though totally the vector field, which corresponds to our system, for this value of the argument is just negative. Therefore, this equality cannot happen. In order to prove the second theorem, we just consider a new function g tilde of mn, which is just e to f of t m squared plus n squared to the power 1/2, and then g mn. And then we write down the system of equations which can be written for this coefficient g tilde mn. So what is important here is that nonlinear part contains just some expression which is similar to convolutions. So when we just write down everything instead of just gmn, then we shall have the equation which has the following form, that this is e minus m squared, m1 squared plus n squared plus m2 squared plus n2 squared, and then minus m squared plus n squared, and then f of t. And because of triangle inequality, this expression is not negative. Therefore, this is less or equal to 1. So this theorem are not the usual theorem in partial differential equations, because they show, first of all, that the inequality, which was just at t equal to 0, is preserved in time. And the second statement shows that it even becomes better. And this is the property of dissipation in our equation. So after the theorem were proven, there appeared a general question: what are other cases when theorems of type 1 and 2 are valid? And the next case, which I want to explain, is just the following. And you will see again why stream functions are sometimes useful. So let's consider the unit square, but write down our stream function psi in the form as it is just h mn sine m x1 sine n x2. And let's consider what kind of fluid dynamics corresponds to this case. So what we have to do is just the following. We shall write down the expression for the velocity. So u1 is just minus delta psi over dx2, and this is the sum of h mn times n sine m x1 cosine n x2. And the same expression can be written for the other component of the velocity. But let's look at this expression. If we just consider this term, then it is clear that when x1 equals to 0, or just 2 pi, then this expression is 0. Therefore, the components of our fluid at x equal to 0 or x equal to pi are 0. Therefore, it means that here on the vertical boundary, the fluid moves vertically along the boundary. In the same way, if we just write down the expression for u2, then the velocity will move along the boundary. This is not very interesting case from the point of view of physics, because here in physics, just when we have viscous fluid, then we usually assume that it satisfies just Dirichlet boundary condition and it is 0. But here just we assume that the fluid moves along the boundary. From mathematical point of view, this is just not bad. The system of equation is just of the same time as before. And in this case, theorem 1 and theorem 2 are valid. So now so now we shall consider more just difficult cases where we shall analyze the same question and the next case is just the case of the unit square with a Dirichlet boundary condition. So just so u is just 0 if x belongs to the boundary of the square. This is one of the most difficult cases in the fluid dynamics. So let's first analyze the situation in more detail. Let's consider incompressibility condition. So let's take again vertical side of the boundary. Then on the vertical side of the boundary, u2 is just 0. Therefore, on the vertical side of the boundary, du2 over dx2 is also 0. But from the incompressibility condition, it follows that du1 dx1 should be also 0. Therefore, near the vertical boundary, u1 should be of order of x squared. And u2 just can be just of order of 1 as a function of x1. And the same can be said about just other parts of the boundary. So if we try to write down the Navier-Stokes system using trigonometric function, then it will not work. Well, for example, if the trigonometric functions cannot give you just functions u1 and u2 with different type of behavior at the boundary. So the way to overcome this difficulty is just the following. We shall consider different bases. This basis is just well known in elasticity theory, but presumably it was not considered before in problems of fluid dynamics. To explain the property of this basis, let's take the interval 0, 1 and consider functions fm of x which satisfy the following equation. The first derivative of m equals to lambda m times fm of x, and also we have the boundary condition fm of 0 equals to fm prime of 0 equals to fm of 1 equals to f prime m of 1. And this is 0. So I shall describe the property of this eigenfunction. But before doing this, I want to explain why this basis is very convenient for our purposes. So we will just consider arbitrary function psi, which is written as HMN Fm times Fn. Then when we consider U1, which is just minus delta psi over dx2 HMN Fm Fn prime. Then because of this boundary condition, U1 will be 0 on the boundary. So if we consider just a variable x1, then it will be 0 because of the function Fm. If we consider the value of the variable x2, then it will be 0 because of this function. In other words, if we consider stream function written with respect to this series, then the functions u1 and u2, which can be written as delta psi of dx1, this is just minus delta psi of dx2, they always satisfy our boundary condition. And this is just, they certainly satisfy incompressibility condition, and they also satisfy boundary condition. So the only one equation which remains is the equation of dynamics. So now let me just explain a little bit more what is the form of this function Fm. So actually what I'm explaining now is contained in our joint paper with Dong Li and Dina Burg, and it was submitted recently to the Journal of Statistical Physics. So the form of this eigenfunction is just the following. So if we omit some remainder term, then it can be written as sine m tilde of x minus cosine m tilde of x plus e minus m tilde of x minus sine n tilde e minus m tilde of 1 minus x. M and m tilde are connected with the following equation. M tilde equals to pi over 2 plus plus tau m minus 1 times exponentially small term, and tau just depends on the parity of m. So the form of this function is just the following, that near the interval 0, for the interval 0 and 1, near the point 0 and 1, they are just small, but then immediately start to grow, and inside the interval 0, 1, they look like ordinary trigonometric function. But then when this function comes to the other endpoint of our interval, it also becomes 0. So these functions are very concrete, can be studied with complete detail. But they have just one very big disadvantage. It cannot happen that everything is good. Something has to be wrong. And what is wrong here is the fact that this function, the product of this function, fm and fn, are not eigenfunctions of the Laplacian. In other words, Laplacian written in terms of this function becomes a non-local operator. And I shall just show you some statement which just explains all this in slightly more detail. Yeah, here it is. Yeah. So the exact lemma which is used here is just the following. Suppose that h1 of mn is just m tilde square plus n tilde square times h mn. And the Laplacian delta psi is written as minus sum of gmn fm times fm. Then we have the expression for this coefficient gmn in terms of h1 fn, and this I shall write it here so that you can see how bad everything is, plus the sum of m tilde square, then inner product of some functions which I can write, but probably not so much needed, h1 mn m tilde square plus n tilde square, and plus the same term which corresponds to the summation over m prime. So this is some kind of integral equation on the plane of indices m and n, and if we have some point m and n, then in order to find the value of new function at this point, we should consider the cross which goes through this point, and then we have just some kind of integral series along this cross. Unfortunately, the coefficients in this series decay quite slowly, and therefore Fredholm alternative does not work here. But nevertheless, something can be proven, and the theorem, the lemma which I want to say is just the following: that assume that h1 of mn is less or equal than some constant a over m to the gamma n to the gamma, where gamma is between 1/2 and 1. Then the coefficient gmn satisfy the same inequality, constant times a over m to the gamma n to the gamma. So it shows in what sense the operator Laplace operator becomes non-local, and what are its properties of the decay. So now I want to formulate the results which conditional results which we have proven in our paper. So we made two hypotheses which I shall not formulate it here. This hypothesis can be checked numerically. It can be just computer-assisted proof of some inequalities, which we did not do. But if these inequalities are valid, then the following theorem follows. Suppose that in our problem corresponding to Navier-Stokes system on the unit square, the coefficients h, m, n of 0 are less or equal than some constant a over m square plus n square m to the gamma, n to the gamma. Oh, I'm sorry, I should write here epsilon, where gamma is between 1/2 and 1, and epsilon is sufficiently small. Then the theorem says that h m n of t satisfies the same inequality, m squared plus n squared, m to the gamma, n to the gamma, for all positive time t. In other words, in the case of the square, there is no exponential decay and only power-like decay. Better to say that we prove the inequalities. And in order to say this, we must have the asymptotics, which we do not have. But in other cases where we try to prove some inequalities, we have just a much better estimate. So we just usually, we believe that this inequality is valid for typical solution of our system. And it shows that in the case of the square, the decay of Fourier modes is much more slow than exponential. It is connected with the fact that the square is not smooth, it has corners, and therefore slow decay of Fourier coefficients is just connected with the presence of these corners. From the general theory of partial differential equations, it follows that the solution to Navier-Stokes system in the case of the square are everywhere differentiable except the square, except the corners. But corners just produce some difficulties. It's probably true for any other domains which look like polygons, where we also can have corners, and there the decay will be also much more slowly. Okay, thank you very much. This is what I wanted to say.
So the questions and comments?
Mm-hmm.
So instead of a square, if you take a circle which doesn't have corners, are you able to find better, like, you know?
Yeah, in the case of the circle, it is known that the solutions are infinitely differentiable until the boundary. Therefore, the Fourier coefficients decay better than any just power, but the exact asymptotic we must know.
Yes, please.
I would like to return to this theorem of Conway, which you mentioned. So it seems it follows from that if there is a point with non-degeneracy, then say take the first point of non-degeneracy, then after it you get non-degeneracy again. So that this would mean that there might be only one point in the interval where this degeneracy occurs, right?
Yeah, I did not mention this. I think that it follows from the theorem that the number of extremal points, maxima and minima, decreases as a function of time. But it does not follow directly from the theory, but it is most likely this is true.
Are there more questions?
What happens, say, if you write, as far as I can see, the viscous term is important here in this analysis. What happens for arbitrary, not mu equals 1, but for arbitrary mu, especially for small mu, the small viscosity, how these results will be? If you tend to 0, tend to earlier equations, how this?
Oh, this is a difficult question.
Did you analyze it?
We were thinking about this, but I prefer not to answer this question.
I have a question about the role. I did not understand the role of the f of t in your theorem when you proved the exponential decay. So it's linear up to a point and then it stays.
Yeah.
But can you choose this point arbitrarily? Or is it given by the...
No, the situation is just the following. That if you take a solution, you have the initial conditions where the Fourier coefficient decays some power. Then immediately for all positive t, they start to decay exponentially. But the exponent depends a little bit on the initial condition. So just, therefore we write the estimates which work until some value of time, and then it just remains constant. So this graph of this function is needed for small values of time.
Okay.
And what is hydrodynamical consequences of this theorem to 1 and 2?
Well, just it says that if you start with initial conditions which have only finite smoothness, then immediately they become real analytic. So this is just
But for 2D Navier-Stokes, you have analytic semigroup, and you can prove this effect directly from equation for velocity.
No, I think it can be.
Because linear path generates analytic semigroup.
No, it does not give exponential decay of Fourier modes. It just gives only.
For Fourier mode, no, not for Fourier.
It gives exponential decay of just a series falling from the semigroup, but not Fourier modes.
Other more questions? No? So thank you again very much.